from Griffith University, and he's going to talk to us about the quantum Fredkin gate.
Testing. Okay. Can you hear me okay back there?
Put it on the other side, because your head will be facing the screen, and that's where your mouth is. There you go.
Is that better? Okay. Hi, everyone. My name is Patel. I'm from Griffith University, as I mentioned. So I would like to thank the organisers, Barry in particular, for organising such a great workshop, and for inviting Jeff initially, who sadly couldn't make it today, but I'll be presenting in his place. And I'd just like to say the discussions have been very fruitful and entertaining and very informative, so I'd like to thank everyone for contributing. So today I'll be talking about an experiment that I've been working on during the first 18 months of my time at Griffith University. It's the quantum Fredkin gate. And I'd just like to say that these are people that have been working on it. So Tim Ralph devised the concept of the experiment and the theory. During the first 2 years of the project, so the project has actually been going on for 4 years, and it's been kind of cursed in a way. There have been a few issues getting it to run experimentally. Frank did a lot of the initial legwork, a lot of the work initially, designing the experiment and doing the initial characterisation. Then after 2 or 3 years, he left. The experiment at the time wasn't actually running, and there was no coherence in the gate. It was operating classically, but there was no coherence in the gate, so it wasn't actually a quantum Fredkin gate at the time. Then I arrived at Griffith University, and I looked at this gate. So my background is quantum dots, so I'm a solid state guy, so I looked at this experiment with a bunch of optics, and I thought, okay, where do I start? The gate's not working, how do I get this to work? So I sort of bashed my head against the table for 3 or 4 months. I couldn't get it to work, and so I sort of made the executive decision to just wipe the table clean and just start over again. And so with the help of Joseph Ho, one of our PhD students, we managed to get it running in about a year's time. So, just to give a brief outline of the kind of work that we do at Griffith University in Jeff's group. So, I know there's been a lot of talk on boson sampling and quantum walks, but at the moment, currently, we are still in the regime of just 2 photon interference. So hopefully soon enough we'll be entering the discussions for true multi-photon interference. But so for today, I'll assume multi means 2 or more. 2. Okay. So these are the different areas of research that we're involved in Jeff's group. So we do foundations of quantum mechanics and quantum control. So these are largely experiments we carry out in collaboration with Howard Wiseman, who's also at Griffith University, who's one of the lead theoreticians. And so quantum control is often dealing with sort of state purification, and you may already know that just in previous years has worked on noiseless linear amplification. Foundations of quantum mechanics such as EPR steering, balanced fidelities, metrology we've also been working on. We've also been looking at EPR steering in regards to quantum communication and device-independent protocols. But today I'll be discussing, obviously, the quantum computing aspect of our work. Right. So, to begin with, for those of you who may or may not know, what is a Fredkin gate? So it's a 3-bit controlled swap gate that was proposed by Edward Fredkin and Toffoli in this paper on conservative logic back in 1982. So this is just a classical gate at this time. And so it's an interesting paper because it deals with 3-qubit gates whereby you send in 3 qubits. So you send in 3 bits and you get 3 bits out. So no data is erased, and obviously such a gate is reversible and it conserves energy. So from a physics point of view, it feels quite interesting. And so the circuit itself looks something like this. So you have a control arm, you have two target qubits, two target bits, and they can either get swapped or they don't get swapped at the output. Right, and so the matrix operation in that case looks something like this, and that's equivalent to a truth table like so. And when the controller is in state 1 or has a value of 1, swap occurs between the target bits. So that's the sort of classical version of the gate. As I said, it's reversible, and in classical computing, it's considered it actually forms part of a universal gate set in classical computing. That's not the case in quantum computing. As we know, the Pauli gates and the control phase gate forms a universal set, but it's still interesting nonetheless. So that begs the question, so is there a quantum version of the gate? The answer is, or up until the last week or so, I guess no. So the first proposal was by Joe Milburn almost 26 years ago, and his version was an optical version relying on strong Kerr nonlinearities, so published in this paper in PRL. And around the time of, in the early days of KLM, this paper was heavily cited because they'd often compared nonlinear optics to linear optics, and this paper would always show it. So his gate looks something like this. It's essentially a Mach-Zehnder interferometer with two Kerr mediums embedded in each arm.
There was actually a paper just before by Yamamoto. You know that one?
Right.
It was a conference proceeding, but it beat this one by weeks or something.
Oh, right, okay.
Yeah, everybody forgets, but Yamamoto's paper was first, but it's only a few paragraphs.
I'll have to try and look at it.
I'll get a reference, I'll give it to you.
Okay, thanks for that. So this is Milburn's version of the gate. And obviously with nonlinear optics, it's very hard to realize in the lab to generate these nonlinear interactions. So obviously people started looking at linear optical proposals. And there've been a few. So in 1996, there was this paper by Smolin and DiVincenzo. They claimed that 5 2-qubit quantum gates are sufficient to produce a Fredkin gate. And then a few other papers came out in the mid to late 2000s. So a paper by Furshek and also a proposal by Tim, Ralph, and Gond, I think is in the audience over there. And there's also this another paper by Furshek. And yesterday, Shijie mentioned that he's also implemented a C-swap gate, and his experiment is based off of this paper. And I think the difference between his implementation and this one is that his experiment uses one fewer ancilla qubits. Ancilla photon, sorry. Right, so there is still an issue with all these proposals, and the fact is that they rely on decomposition of the gate into 2-qubit gates, 2-qubit C0 gates or C-phase gates. And given that these gates are probabilistic, the actual success probability is rather low. So if you're trying to do this in the lab, you're going to be counting for a very long time in order to gain the statistics to show that it works. So what we'd like to do is seek another approach, and that approach is this idea that came out of Jeremy O'Brien's group, led by Zhu and Ralph, and it's the idea of adding control to arbitrary unitaries. So the general idea of this is to exploit higher dimensions of the qubit. So expanding the Hilbert space from 2 to 4, whereby two of the dimensions relate to polarization and 2 relate to spatial modes. And so what you do is you send in your photon, you apply a controlled path gate like so. You generate entanglement in such a way that the red modes are entangled with the blue ones, the blue spatial modes, and the blue modes undergo the unitary operation that you want to carry out, and the red ones sort of just bypass it. The problem with this, though, is it seems quite elegant and nice. The problem with this, though, is that the path gate itself requires 2 C0 gates to carry out. So you've essentially still got a bunch of C0 gates to generate this path entanglement. One alternative way to do it, the way that we do it, is to try and generate the entanglement directly from the source itself. You've got these down conversion sources, and they generate polarization entanglement, so you might as well make make use of that.
What is DOF? Spatial DOF?
Degree of freedom.
Degree of freedom.
Sorry.
I was thinking distributed optical fibers. I'm just wondering.
Okay. Right. So essentially, what we'd like to do is do something like this, where we have our C-swap gate, and we send in one in the control, and it swaps the values of the two target qubits. And then what we want to do is we want to arrange the modes in such a way that it bypasses this. So if we send in 0, then we don't get the swap operation. Right. So our scheme can be sort of illustrated in this figure. So what we have is we have two SPDC sources, and each source emits 2 photons either in the red modes or the blue modes for the first source, and the second source either emits 2 photons in the green or the yellow modes. And so what we do is we carry out some state preparation here, so we initialize the states here, and we erase the path information to generate the spatial mode entanglement. And the idea behind this is that this rail corresponds to the control, this one corresponds to the first target qubit, and this one to the second one. And we simply swap the spatial modes so that if the photons are present in the blue modes and the green modes, then when we measure the appropriate polarization of the control here, then that projects the gate in such a way that the swap is carried out. And if the photons reside in the red and yellow ones, then it just carries out identity, so nothing gets swapped. And finally, we have just a photon which we use to herald the success of the gate, successful operation of the gate. Right. So mathematically, it kind of looks like this. So we have our SPDC sources emit pairs of entangled photons into these modes. Blue, red, and green. We mix them in such a way that we generate spatial mode entanglement of this form. We can encode arbitrary polarization states in the control, target, and target 1 and target 2. And then we take this and we only apply the swapping method to the blue and the green modes, and such that in the logical basis, when the gate acts on the qubits, we get a swap here, but we don't get a swap when we measure the polarized photon in the control. Right, so the experiment looks something like this. So we use a standard TISAT laser, tsunami. It emits a pulse. We pump an LBO crystal, which frequency doubles the light. We filter the light. So we're left with just the UV, and then it passes through some optics. We pump a down conversion crystal, and it produces these characteristic type 2 type cones, and they're emitted in these spatial modes that I mentioned in the previous slide. So 2 photons in the blue modes, or 2 photons in the red modes. And then the same UV pulse will then pump the second crystal, which produces photons in the other modes. And so this is what the experiment looks like. This is what the entire experiment looks like. So we have the source, and we have this section is our gate essentially. So if we just focus on the gate for now, so the gate consists of essentially 3 interferometers. We have a control arm, which is a beam displacement interferometer, and then we have 2 displaced Sagnac rings. So each Sagnac ring corresponds to a target qubit. So the output of which will correspond to target 1 and target 2. And then we have a trigger down here. So looking at this, you'll notice that 1, there are no 2 qubit gates in this. There's just local unitary operations, single qubit. There are no ancilla photons in this. We just have a trigger to herald the success of the gate. And so in terms of the actual success probability, for this particular implementation, success probability is 1 over 16. And that's largely due to the fact that our source is capable of emitting, say, 2 photons in the red mode and then 2 photons in the green mode, and that would mean that the gate isn't successfully operating. So there's a 50-50 chance that the photons are emitted in incorrect modes. So So if we were actually to look at the probabilities, if we consider that this displays Sagnac ring here and this one here, we're only collecting from one of the outputs, so we actually throw away some of the counts. So if we were to actually place a detector here and place one here somehow, then we'd actually be able to boost this up to 1/4. But at the time we didn't have sufficient detectors and optics, so this is just a close-up of the control arm. So we separate the two spatial modes of the control. We encode twice, so we encode the control, the value of the control on both of the modes, and the same value on each mode, and then we coherently combine them at the output of this beam display. So we have a phase fixer here, which I'll come to later, and then we have just standard tomography setup, and likewise a close-up of the Sagnac ring. So we have a special beam splitter here, whereby half the interface is a polarizing beam splitter, so that separates the photons according to their polarization into these spatial modes. And then the other half of the beam splitter is just a non-polarizing 50-50 beam splitter, which we use to sort of erase the path information and generate our spatial mode entanglement. And you'll see in each of the two modes, each of the two spatial modes, we have a 1/2 and 1/4 waveplate to carry out state initialization. So we initially do just some basic characterization of the sources. So for each source we measure 2 qubit density matrices. We calculate fidelities of 98, entanglement about 95, and purity is about 98. Actually, for a while, only one of our sources appeared to be working properly, and we were actually getting much lower values for the second source, and I couldn't figure out why that was the case. And I spent one afternoon just staring at the table, just trying to work out why it wasn't working, and then I just had a suspicion that the mirror may be dodgy. So I asked Joseph to characterize that mirror, and it turns out that that particular mirror was dropping this purity down by about 10%. So ever since then, I tell every student when they're setting up an experiment, characterize each and every mirror, because every mirror is not created equally. There's definitely a discrepancy amongst them. So we have done a 2 qubit characterization, and we've also measured the Hongu-Mandel dips at the outputs of each of the Sagnac rings, and we calculate visibility about 90%, which is sort of typical for these types of SPDC sources. So we have a good indistinguishability and good erasure of the path information. So then what we do is we carry out measurements of the actual truth table. So we're measuring the outputs of the gate in the logical basis, and the result looks like this. So we have inputs here, and we have outputs. And when we measure the 4-fold coincidences, we see that there's a swap occurring. So if we send in 101, then we get out 110, for instance. And then we can calculate this gate fidelity, which Andrew White likes to call the inquisition. And we measure a value of 96 plus or minus 4%.
You like to call it the what?
The inquisition.
The Inquisition?
Yeah. I read it in one of his papers and thought, okay. So this is a fairly high value. Actually, so this value is only limited by the polarization optics in our gate. So this measurement is actually just photons being routed along different paths in the gate due to the polarizing beam split. There's no actual quantum coherence going on here at the moment. So if you were to actually maybe obtain better polarization extinction optics, then you might be able to bump this up closer to 100%. So obviously we're interested in the quantum operation of the gate. So what we'd like to do is send in a superposition in the control arm, and essentially prepare the gate in a superposition and swap and no swap. And so if you recall, this is our starting state. This is the input state of the system, and we want to prepare the control in a superposition or diagonal polarization. And once you do the expansion, so if you expand this out, if you expand out the control and if you expand out the trigger, so with the trigger we actually send the photons through a half wave plate at 22.5 degrees, which prepares a superposition, and then we pass that light through a PBS and we use that as a trigger. So that we do this just to erase the path information in the trigger arm. And so once you do this expansion, you get something like this. And then it turns out that we've actually, the way our control interferometer is configured, we actually dump these two, we actually dump photons corresponding to these two terms. And so when we coherently recombine the light at the output of that interferometer, we end up with something that looks like this. So when we detect a trigger that's H polarized, we measure this state, and if we measure a trigger that's V polarized, we measure this one. So there's just a pi phase difference. And so what you can see is that if we take this arbitrary, if we take these arbitrary states and prepare H or V of the H, we generate GXZ states. And so here are some of the results. So in the top panel we have what I call the GXZ1, which is 010 with 101, fidelity of 88%, fidelity of about 80%. And so the Fredkin gate itself can generate 4 of the 8 maximally entangled GXZ states. If you want to generate the other 4, you have to carry out a local unitary somewhere after the gate. So we've measured the 4 states, so these are values, so here are the values for 2 of them, so 88, 90, and then we also have the other 2 values, which are 93% and 51.7%. Just summarizing the table, so just to give you some statistics, our 4-fold rate is around 2 a minute, so we could probably bump this up to 8 if we had more detectors. For each of these measurements, we ran it for about 36 to 48 hours. And we measure a total of about 5,000 fourfolds, which seems to give us pretty good statistics and reasonably low error. And so after we did these measurements, I sort of trawled through the literature to see what are the highest fidelity values for photonic GXZ states measured by quantum state tomography. And I came across this paper by Thomas Yanovide's group, where they directly generate GXZ states from their sources, and they claim that their value of 86 is the highest. So with our value of 93, we've surpassed that. So. And I'd just like to say, no, we haven't carried out full process tomography on this gate. Our count rates are just too low at the moment. Right, so given that we've carried out quantum state tomography, it turns out that if you extract some of the measurements from that set of data, you can actually calculate maximum values for the evaluation of Mermin's inequality, which looks something like this. So we know that GHZ states can show strong contradiction between local hidden variable theories and quantum mechanics. This is work that Zalmi did many years ago. And so we take our data and we want to see what sort of valuation we could potentially get. And so if we measure a Mermin parameter Sm of greater than 2√2, that also confirms that we have genuine tripartite entanglement. So we did that, and here are the results. And we measure Sm 3.58, which is greater than 2. So, and it's also greater than 2√2, so that verifies genuine tripartite entanglement. Right, so what Mermin's inequality can't do is it can't discount non-local hidden variable theories for tripartite systems. So a few years ago, Svetlichny came up with his own inequality, which can verify this. So the reason why Mermin's inequality is insufficient is because it can be violated for arbitrarily strong correlations between just two of the particles. Whereas Svetlichny's inequality takes into account genuine tripartite entanglement amongst three particles. And so his inequality looks like this, and we carry out a similar set of measurements. So we measure the Pauli basis and a rotated basis. And so we're looking to get a value of greater than 4, with a maximum possible value of 4√2. And we measure 4.88, which is a violation by 7 standard deviations. So that confirms that the state could be capable of violating non-local hidden variable theories if one were to try to do that in an experiment. So finally, what we wanted to look at was we wanted to look for an application of the Fredkin gate. So it's only so good having a gate and do some characterization, but what can you use it for? And one of the simplest applications is actually this one. It's the direct estimation of nonlinear functionals. It's a paper that Arthur Eckert published back in 2002. And also around the same time, Brad and Philip also published a paper in, I believe, in PRA, which sort of touches on the same sort of subject. And so the idea is that you have a simple quantum network that can directly estimate properties of a quantum state without recourse to quantum state tomography. So as we know, QST can take a long time in the lab, and it would be nice to have a method just to directly measure some of these properties. So the circuit looks like this, so it's our Fredkin gate, and instead the control arm basically looks like this. So we have a Hadamard phase shifter, and another Hadamard, so it's essentially a Mach-Zehnder interferometer embedded in the control of the circuit. And it turns out that if you were to perform this, then when you perform this calculation of trace of the unitary times rho times rho for some arbitrary quantum state and the targets, the fringe visibility of the output of this interferometer corresponds to trace rho. And so that quantity, obviously, if you set rho T1 equal to rho T2, you get the measure of the purity, and if those two states are different, then you get a measure of the orthogonality of the two states. And so just to remind you, this is what the control arm looks like. So what we do is we essentially turn this into a Mach-Zehnder interferometer by setting this to this state initialization to prepare diagonally polarized light, and then we set this measurement stage to measure diagonally polarized light, and we tilt this half-wave plate to tune the phase and give us a set of fringes. Right, so if we prepare each target qubit in such a way that the polarizations are the same, we measure this black set of data. So we clearly see fringes for states that are parallel. And we measure visibility of 82. If we start to introduce some orthogonality to one of the qubits, so if we prepare H and D, we get the red curve, and visibility of about 50%. And if we try and make them fully orthogonal, then we get a visibility of about 5%, which should be 0. So I must say that the reason we don't get 82%, the reason we don't get 100% visibility when we set them to parallel is simply because, one, our Hongu-Mandel interference visibilities aren't ideal in our Sagnac interferometers, and two, when we send in classical light through the control arm, we don't get 100% classical visibility, we get about 95%. So these factors contribute to this outcome. So that's an overlap measurement of two quantum states. We then perform a set of measurements trying to calculate the purity of the quantum state. So it's this quantity here. And so actually preparing mixed states in the lab is quite a difficult thing, especially in our setup, which is quite compact and it's a passive system, a passive circuit. So what we do is we measure a set of pure states. So we measure we measure fringes corresponding to the target qubits in HH, HV, VH, VV individually, and then we add the data in post-processing to simulate the effect of mixture. And so this parameter M corresponds to the degree of, I guess, the degree of purity, if you like. So we're going from 1 to 0, and we see that as we increase the mixture, then we see a reduction in fringe visibility, which confirms that the gate is doing what we expect it to do, the circuit is working, and we can get an estimate of the purity from these measurements. And so that's it. So just to summarize, we present the first demonstration of the quantum Fredkin gate. At the time, I thought it was the first, then I realized about a week ago that CJ's also worked on this and has successfully implemented it. So it's one of the first demonstrations of the quantum Fredkin gate. So we use entanglement as a resource for reducing the overheads and to increase the probability of success to 1 over 16 compared to previous schemes, which were about 1 over 100. And we've measured the truth table with fidelity of 96%. And we generated high fidelity, the highest fidelity photonic GSS states verified by quantum state tomography. And we've also shown that these states should be capable of violating some local and non-local hidden variable theories. And we've also put it to the test of applying it to Arthur-Eckert's network for measuring the overlapping purity, and it seems to do what we expected it to do. So in terms of future work, we can actually extend the gate to 4 qubits by replacing our trigger with another Sagnac interferometer. And in doing that, you can produce a permutation gate. So that's something that Joseph is going to be working on probably next week, actually. And so finally, if anyone has any other suggestions or any other quantum information protocols that people come across who may know anything about applications for Fredkin gates, I'm always curious to hear from you. And finally, we're submitting this paper very soon, hopefully in the next couple of weeks. So thank you very much.
So I want to thank you first for the very nice talk.
I was slightly 2 nanoseconds ahead of Barry. So I have a suggestion. There's an old paper by Chris Carey from 2001 or 2002 PRA where they use a Fredkin gate as a heralded Newton state generator.
Right, okay.
And so you say, what is suggestion? So go read that paper and make Newton states.
Okay, good. Duly noted. Thank you.
Okay, so, thanks. So the other one, of course, that's extremely important for the quantum optical Fredkin gate has to do with distributed quantum computing and particularly quantum communication protocols.
Okay.
For example, quantum fingerprinting. Do you know about this?
Yes, I've come across fingerprinting.
So, and these have been written about for years. So the idea has been in quantum fingerprinting that the alternatives have been found, specifically because there's no quantum optical Fredkin gate.
Yeah.
So you know about it, right?
I've done some reading into the fingerprint.
So why did you not pick one of the most important elusive reasons for the gate that people have been talking about for 10 years?
You mean actually experimentally implementing it?
Well, yeah, I've worked on this myself, that we haven't had so the whole idea of the Fredkin gate, the controlled swap, has applications there. It could be useful for fault-tolerant quantum computing. So I think the work is wonderful, but then I was disappointed at the end with the exam. You know, you found one of the least interesting applications, in my view. The people who wrote it aren't here, so I can say that.
So this project has been going on for 4 years, and the Centre of Excellence, a lot of pressure to try.
So
and
you got worn out.
So I just wanted to knock it out.
You want to knock it out. Okay, so you're writing it up and submitting the next couple of weeks?
Yes. Yes.
Okay. What? What'd you say?
Still have time.
Still have time. Okay. She's the next one.
Sorry.
No,
Is that
go
okay?
ahead,
Yeah. It just follow this up. This controlled swap can be used to estimate the inner product. Or maybe the same thing, was it?
No?
Oh, okay.
Oh, I get it.
The inner
It's a
product.
distinguishability test.
Yeah, that's right. And
That's
people use it for quantum intelligence and whatever do you want to call it. It's wonderful.
I'm the chair.
Any other questions or comments?
Oh, yeah, quantum machine learning.
Okay. She has another one. Yeah. So lots of suggestions for you, that's for sure.
Are you taking notes?
It's all
There. But
It's
then
all-
you're
it's all video as
going
well.
to beat your head on the table and forget everything.
I'll wait for the 4 qubit.
The animations were wonderful.
Oh, thanks.
Yeah.
I noticed how none of the optical elements actually touch the table, they just float in the
Yeah,
air.
that's how it
That's
really
quite
is.
a trick.
Well, I did put this in, but it just took too long to render, so I just got it.
Okay.
I did it on my laptop, it took too long.
Any other questions, comments? If not, then let's thank both the speakers of the session and of course the whole lecture. So I think Barry has a few comments.